Okay, next I will consider, like, my system consists of n particles. Okay, my system consists of n particles with masses m1, m2, m3 up to, let's say, mn. This is another particle, last particle. Okay, its mass is mn. Now the total mass of the system is I write the total mass by, I represent the total mass by capital M, which is equal to the mass of individual particle, like m1 plus m2 plus m3 plus up to mn. I can write it in the form of summation. So we have I started from 1 up to n mi. This is the total mass of the system. Now we have another concept of center of mass. First I will define the center of mass, what it means. A center of mass a center of mass of a system of particle, I can write it is center of mass. Cm means center of mass of system of particle is a point in the system. Okay, is a point in the system where the whole mass of the system is distributed, where the whole mass of the system is distributed at that point. Like, if we have a rod, let's suppose we have a rod. Okay, if I hold this rod at this point, then this rod will rotate in this way. If I hold this rod at this point by using my finger, okay, then this rod will rotate in this way. But there is a point where if I put my finger like at the center of this rod here, then it will remain like this. It will neither move in this way nor it will move in this way. But if I use my finger like this, then the rod will stay like this. So this is the point where all the weight of this rod is distributed. This point is called center of gravity. Similarly, in this rod we have a common point where all the masses of the system is distributed. That point is called center of mass. Like, if I have a regular shaped body, okay, if I have a regular shaped body, let's suppose my body is like circular, okay, then the center of the mass is always located at the center of this circle. Okay, the center of mass will be somewhere here. If I have a rod, if I have a shape like this, then the center of mass will lie, if I use this diagonal line and these two diagonal lines where they cross each other, then the center of mass will lie here. So if I put my finger here, then it will remain, I can say that if I put my finger somewhere here, then this body, it's neither move in this way or it's neither move in this way, but it will remain stable at my fingers. So that point is basically called center of mass. Now the position, like, this is my system of particles, okay, and I have my center of mass is somewhere here. The position of center of mass is represented by this capital R, okay, and this position is represented by this formula. This is a well-known formula, okay. the position of center of mass, which is equal to sum over I mi ri over sum over I mi. This is the position of this, I can call it position of center of mass. Okay. Now here this summation over I mi, this basically represent the total mass of the system. Okay, so I can write it as like this: R is equal to sum over I mi ri over m. I can use more simplified form, like if I bring m to this side, then I have mr is equal to sum over I mi ri. Now if I put this equation here in this equation, d square over dt square, and instead of this summation over I mi ri, I will use mr, okay, which is equal to sum over I fi external. Okay, this is the total external force acting on the system. Now I can simplify it, and I can write it in more simplified form, like I will bring this side to this side. Summation over I fi external is equal to d square over dt square of m r. This is capital M, okay, where this capital M is basically sum over I mi, and this capital R is sum over I mi ri over m. These are the two equations for the center of mass. Now here I will drop this summation here. Now fi external, if I drop this summation, then I have only f external, okay, which is equal to d square over dt square of mr. Now here this f external basically means sum over I fi external, and as the total external force acting on the is the total force acting on the system of particle. Now the momentum of center of mass will be P, like the momentum of center of mass is, the cm means basically center of mass, is P, which is equal to sum over mi vi, because momentum is basically represented by mv, but we have a center of mass, so I will use this summation here. I can write it is like this: sum over I mi dri over dt. If mass mi is constant, then I can bring this mi inside I can bring this mi here to this derivative if mi is constant. Okay, so we have summation over I d over dt of mi ri, because if mass is constant, then I can keep it outside of this derivative. So we have again the same equation. I can write it is like this: I can bring this derivative outside of this summation, d over dt sum over I mi ri. But we know that sum over I mi ri is basically what? mr. So it means the momentum of the system of particle is d over dt of mr. I can write it as P is equal to m is constant, okay, mass is constant, so I have m dr over dt. This implies that P is equal to m r dot. If I take p is equal to m r dot, if I take derivative of both sides, dt over dp over dt, then we have d over dt of m r dot. We have p dot here because dp over dt are represented by p dot, which is equal to m, and we have d r dot over dt, which is basically r double dot. Now if I use this equation, this one, let's say this is star, if I use this equation and where, if I use this equation here, my f external is this, yes, this one. If I use this equation, now basically this equation is f external is, if I write this equation, okay, f external is basically d square over dt square of m r, okay. So m is constant, so we have m d square r over dt square. So we have m r double dot. This double dot represents double derivative with respect to time, okay, f external. Now if I use my this star and this double star equation, using equation star and double star, we have what? P dot is equal to f external. Now here I have two important equations. Now one is this one, okay, I represented by this steric now, and one equation is this one, yes, this one. Now this equation steric and double dot, double cross equation, this one, these two equation shows that in the case of system of particle, okay, in the case of system of particle under the action of external force, action of external force, the center of mass of the system, the center of mass of the system behave like a particle, okay, whose mass is equal to the total mass of the system, and is acted upon by total external force. F external. This statement basically means that if we have a system of particle, okay, let's suppose we have n particles in this system, like particle 1, 2, 3, 4, and we have nth particle. There are n particles in this system, okay. This statement basically means that if you are going to study the forces, the effect of forces on each individual particle, then you have to sum all the forces acting on this individual particle, and you have to calculate the total external force, okay. This is one method. And the other method is, if this is the system of particle, then you have to calculate the center of mass of the system of particle. Let's suppose the center of mass of the system of particle is somewhere here, and then you have to calculate the effect of the external force on this center of mass of particle. Then both the situation will give you the same answer or the same result. Like, you have to calculate the effect of external force, F external, on this whole system by calculating the effect of this external force on individual particle, and then you have to sum up all the external force and get the total external force. This is one method. And the other method is you have to find out the center of mass of this system of particle. Once you find out the center of mass of this system of particle, then calculate the effect of this external force on the center of mass. The result you will obtain from this one or the result you obtain from this one give you the same result. So this is more simplified form. Like, to simplify the problems of a system of particle, then first we have to calculate the center of mass, and then we will see the effect of external force on the center of mass. Then this method, this procedure is more simple as compared to calculate the external force, the effect of external force on individual particle. Now, here we see that the motion of the center of mass of the system is independent of internal forces, because external force here, we have only the external force here, and similarly we have only the external force here. So there is no internal force involved in these two equations. So it means that the motion of the center of mass of the particle center of mass of the system is independent of the internal force. Now, if the external force is zero, if the external force acting on the system of particle is zero, like there is no external force acting on this system of particle, if there is no external force, then we have P dot is equal to 0. From this we can say that P is equal to constant. Now this shows that the total momentum of the system of particle is conserved if the total external force acting on the system is 0. I can write it here. Like, after this I have to write this statement that this shows that the total momentum of the system of particle is conserved if the external force acting on the system is 0. And if there is no external force, then the total momentum of the system will remain conserved. So I will stop my video here. In the next video I will move towards the angular momentum of the system of particle. Thank you.